open paren, fluid, closed paren. And just like before, I don't want you to think that you have to have a fluid to have convection. Fluid says, oh yes, something can flow here. Material can flow. Indeed, ladies and gentlemen, remember my initial experiment when I was talking about conduction? And heat conducted up the rod until I couldn't hold it anymore, and then I threw it over there like that. Okay? That was convection. Because I heated the material, and then I threw the material over there, so I moved the heat from here to there. That will fit under the definition of convection. Humorous, but true. Okay? So we convected heat by heating something and moving it. Conduction and convection. Oh, wait a minute. Somebody in this room could make an argument. Let me start the argument and see if anybody in this room can finish it. Okay, think about this. Try to figure out what my point is and try to finish my argument. Somebody in the room could say there must be at least one more form of heat transfer because. You fill in after the because.
The sun.
Heat transfer is gas.
How do you know?
Because we're not dead.
Space.
We're not dead.
He's close. Help him out.
Heat travels from the sun to the earth through space.
There you go. Heat moves from the sun to the earth every day, and there's nothing in between. There must be at least one more form of heat transfer because the previous two definitions, conduction and convection, both require a material medium. And yet we receive heat from the sun every day, and there is no material medium. Yes, there is one last form of heat transfer. What's its name, please?
Radiation.
Radiation is the movement of heat as an electromagnetic wave. The third form of heat transfer, radiation, is the movement of heat as an electromagnetic wave. Your parenthetical statement would be vacuum. And to finish my original statements, I would say, no, you don't have to have a vacuum to have radiation. The implication is simply that you don't necessarily need a material medium to have radiation. So, personally, all I remember is conduction, convection, radiation, solid, fluid, vacuum. That's all I remember. And then I remember, oh yes, solid. When I think the word solid for conduction, that means nothing moves but the heat. When I think fluid for convection, oh, this is where I'm moving the hot material medium. And when I think vacuum, how do you move energy in a vacuum? There's only one way, electromagnetic radiation. So instead of trying to remember all those words, what I would do if I were you is simply remember conduction, convection, radiation, solid, fluid, vacuum. Christine.
So, sorry, just to understand it a little better. Heat is an oscillation, right? Heat is an oscillation of something.
The measurement of temperature is the measurement of oscillation of something.
Okay, so then that's why radio waves, or that's why waves can cause heat, because waves oscillate, and so they're causing something else to oscillate. But obviously the waves are oscillating at a higher frequency than normal material that would give a temperature change. So how do we get the waves to slow down?
No, not obviously. Let me start with this, to be specific. Heat is the movement of thermodynamic energy. And conduction, convection, radiation are different ways of moving energy around. Now, she accurately says, now you've got this oscillating, this electromagnetic wave that's going to strike a material and cause it to vibrate. But the frequency of the oscillation of the wave depends on two things, not only the speed of the wave, but the wavelength. Let's take, for example, visible light. Visible light wavelength is incredibly small, and the speed is tremendously high. The frequency is on the order of 10 to the 14 hertz. Visible light, when it goes by, the frequency of the light is on the order of 10 to the 14 cycles per second. And of course, the material in this room is not oscillating at 10 to the 14 oscillations per second. That's why light typically does not directly heat things up. If you want to heat up something, like let's say in a microwave oven, then you use a much longer wavelength. And very often what happens is that electromagnetic wave excites the electrons jumping from level to level create a resonance in the molecule. That's why microwave ovens work the way they do. The microwave oven does not heat the environment, it only heats materials typically that have water in them. It has a frequency that is sympathetic to water molecules. The microwave passing the water molecules is absorbed by the water molecules and eventually through electron interaction is converted into thermal activity. So it's not an immediate thing, it's not a 10 to the 14 cycles per second is going by, therefore the atoms start to vibrate at 10 to the 14 cycles per second. It usually is an electron interaction which eventually causes the molecule itself to vibrate through collisions. So, it's not as simple as it sounds, but it does happen that way. Good question. Are there others? Questions, comments, cares, or concerns? Let me give you kind of a broad definition of things here, or maybe not so much a broad definition, but a broad comment about this class. Conduction of heat is an extremely important topic in engineering. It's an engineering topic. Very important. Let's take, for example, civil engineering. Maybe this room. Why is conduction important in this room? Or better yet, take this room and move to Minnesota.
You just said it.
We have to calculate, for example, how much heat to put in this room. What's the rate of heat inflow into this room to compensate for heat loss, which is going in what direction? One direction only, yes, out, but that wall right there. So we have to understand how that wall conducts heat out. It's a concrete wall, it's got windows in it, it's got a door in it, and presumably all the other rooms around us are at roughly the same temperature we are, so there's no real heat communication through the walls or the ceiling. And of course the floor gets saturated with heat, so there's no real heat loss after you initially heat the floor. It's only that wall over there. So you have to study that wall and understand the conduction of heat. So the people, I'm not sure who they are, but the people who design the HVAC, the heating, air conditioning, and ventilation system, are very concerned about conduction of gross macroscopic amounts of heat through walls, and if it's a single-story building, through the ceiling and so on, or through the roof and so on. Or better yet, let's say you're designing computers. There are components in computers that get warm. You've got to set the heat off. You've got to remove the heat, dissipate it to the environment, or you'll melt your computer. So sometimes you have to know about thermal conductivity and build heat sinks right into your system so that the heat generated while this electrical equipment is operating can be dissipated safely without causing internal damage. There's a lot of very important reasons to very carefully understand conduction of heat. Everything from gross macroscopic building construction to electronic component construction and everything in between. The next topic, convection. It's important in a science. Can you guess which one? Meteorology. The meteorology of this planet is essentially a study of convection. Convective currents are what cause the weather. The planet, generally speaking, is heated more at the equator than it is on the poles. That causes convection currents. That moves air and brings with it thermal energy and moisture, precipitation, storms, etc. Convection is a very, very important topic in meteorology. But I must say, ladies and gentlemen, convection is a very complex topic. It always depends specifically on the system that you're studying. Whether it be the convection of heat in boiling water, or the convection of air on this planet. It depends specifically on the size, shape, structure, and heating elements. So it always tends to be a very complex story, which we will not treat in this class. We'll mention it, we'll pay respect to it, and we'll move on. Although I will say one thing to you that I don't know if all of you have declared a major yet, but I was certainly surprised when I was a student. I didn't think that the study of meteorology would be very interesting at all. And then I was forced to take a class in meteorology. I would not have done it had I not been forced to take a class. And about 1/3 of the way through the class, I found it to be fascinating. I was deep into my major at that time, or I may have considered meteorology as a major. 2 reasons. One, it's a fascinating and young science. They haven't had their Newtons or Einsteins yet. And it's one of the most practical sciences that we know of. Meteorology affects everybody every day. There's always going to be a job for meteorologists. The farmers have to know about meteorology, the pilots of the airplanes, the ships at sea. Everybody has to know about meteorology every single day. It's a new science. There's going to be a lot of funding in that area, and I think it's very, very interesting. If you have not yet declared a major, and even if you think, like I did, oh, meteorology, how boring. It ain't. Take the class. It's not a boring class at all. You might find yourself in the same position I was in, totally surprised at how interesting meteorology is. It's a great class. There's a lot of potential employment in the very near future for meteorologists. Okay, so we've talked about those two. Now, radiation. I consider radiation the principal physics topic. That's the one we're going to concentrate on. Why? Because it illuminates, if you will, the study of optics. That's kind of a bad pun. But it does. It illuminates optics. And it's the key reason that we will change from classical optics into modern 20th century physics at least. So radiation is really the key issue for this class. So when we start talking about these things, we'll talk reduction, we'll pay respect to convection, and we will concentrate in radiation. The study of radiation by Max Planck changed the entire world just a little over 112 years ago. 112 years ago, the study of radiation by Max Planck created 20th century physics and everything we enjoy today. Everything we enjoy today, all the engineering that we enjoy today, from just the lights in this room to the computer on your desk, all of it was made possible because of radiation. So that's the one we're going to concentrate in. Any questions or comments about that? Electromagnetic radiation, as I implied a few moments ago, considers a much larger area than just visible light. Probably from your Physics 5 class you learned that light was electromagnetic radiation. And by the way, did they mention who demonstrated that? In about 1856, James Clerk Maxwell was the one who finally discovered that light was electromagnetic radiation. So that was a key topic in your Physics 5 class, but it covers a lot more than just visible. Electromagnetic radiation goes from the very, very long radio waves to the short radio waves, microwaves, infrared. There's a very narrow band that we call visible light. Then beyond that, there's a large band called ultraviolet, X-rays, gamma rays, cosmic rays. They're all the same thing. The only difference is wavelength. Visible light has extremely short wavelengths. By the way, I just mentioned something here. Visible light has a range of about 300 nanometers to about 700 nanometers. That's the wavelength of visible light. And you're all familiar with nanometers, of course. That's 10 to the minus 9 meters. Have you seen this before? 3,000 A with a circle over it to 7,000. What's that unit?
Angstroms.
That's correct. That's an angstrom. 1 angstrom unit is, now I think it's obvious, 1 times 10 to the minus 10 meters. So I say that because in this class I very often switch back